We're ready to go after a little bit of technical difficulty. If you don't know, Michelle just rejoined us after being away on a NOAA research vessel for several weeks. So she is fresh back with us from some ocean research. So her computer is probably still a little seasick, I guess. So we'll get it back to it. But we've got it working out. So you'll be hearing Michelle's voice through my computer, but she is the one talking. So Michelle is a PhD research working with myself and Dr. Petra Klein, also on the Tracer Cubic project, which you heard about earlier this semester from Francesca Semesta. But it's nice to have both of them working together on that. Michelle comes to us with an MS from the University of Wisconsin-Milwaukee, and she earned her bachelor's degree at the Metropolitan State University, Denver. Michelle has lots of interesting stories from her time and study. She's always a fun person to talk with. She has a different perspective on a lot of things. So if you don't know Michelle, I encourage you to get to know her. She's a joy to work with. But with that, I will let her take it away.
Thank you, Liz. Thank you all for coming today. Like she said, I've been away for about 5 weeks, so this is actually my first day back in the building. It's happy to see some people, walk on land again. As a result, I was not able to attend other seminars, so the beginning of this might feel kind of like deja vu to what Francesca did, but it'll be fine. We'll get through it. I'm going to be talking about sea breeze events near Houston during the Tracer Cubic campaign. So to start off, I just wanted to hit my acknowledgments right away. Many thanks to everybody for getting this campaign going, getting it knocked out, and the initial data analysis stages. Drs. Klein, Smith, Bell, and Gebauer, as well as Francesca and other collaborators. Huge thanks to you guys. To the University of Houston for allowing us to set up clamps at the Coastal Center. Of course, all my family and friends for their never-ending support, and my cat Bear, who always gives me love after a long day. And of course, the grant as well from the DOE that is funding this work. Now, to get us started, I just wanted to do your basic review of what the atmospheric boundary layer is. I'm sure that we are all familiar with and have seen at least some version of the figure on the right-hand side, which is really just depicting your diurnal evolution of your typical ABL. Shortly after sunrise, your ABL height quickly increases as convective heating takes place and turbulence occurs. After the sun sets, your ABL height lowers and the layer becomes stable with a temperature reversion above the surface as the ground cools faster than the air above it. The figure here on the left-hand side is from Clamps 1, which was located just north of Houston. As you can see, shortly after sunrise, we experience relatively strong updrafts and downdrafts that act to convectively mix the layer. These turbulent motions quickly diminish after sunset, and you can see a buildup of aerosols within the now stable boundary layer, as well as in the residual layer that's located about 1 kilometer above the Earth's surface. The ABL is an important portion of the atmosphere as it is directly impacted by the Earth's surface, and it acts to transfer different properties like temperature, moisture, and momentum. Now, in areas near the coast, like in Houston, Texas, the ABL diurnal evolution gets a little more complicated, as you have a combination of continental and marine boundary layers interacting with each other. The marine boundary layer is shallower than the continental layer since the air-sea temperature difference is less than what is experienced over land. Additionally, marine boundary layers will have greater wind speeds due to decreased friction, while slower wind speeds are observed in continental layers due to the increased surface roughness. Like other aspects that we see in different parts of meteorology, circulations are induced to try to create a balance between these two very different layers. Along this important coastal area, sea breeze circulations develop, and again acting to equilibrate the interface area between the continental and marine boundary layers. The sea breeze circulation forms as the land heats up after sunrise. As we know, the land will heat faster than the water, and this heating leads to rising motions and the development of lower pressure. As a result of the rising motions and development of lower pressure, pressure gradient force forms and acts to create an onshore flow. This onshore flow brings cooler, more moist and stable air over the land from the ocean, which is depicted by the sea breeze front in the upper panel of the figure on the left-hand side. In order to conserve mass, there is a return flow above the sea breeze front and descending motion over the ocean that acts to help close this circulation. As the sea breeze front is forced on land, areas of enhanced convergence can occur, which can help to induce convection initiation or CI. The sea breeze front also has effects on the aerosol content within the atmosphere. Depending on the strength and location of the front, it can act either as a ventilation mechanism in which we lift the aerosols high enough to be caught in that return flow and taken out over the water, or on the other hand, if the layer is really stable, it can actually act to trap these aerosols near the surface, which can ultimately have serious health impacts on the population, especially for people who have pre-existing conditions such as asthma. So you might be wondering, why do we really care about this? Right now, there's still a lot of work, a lot that we don't necessarily know about the sea breeze. We can often visually see it either using radar or satellite imagery. We can sometimes depict it with numerical weather prediction models via wind shifts and temperature gradients, but we don't really know the typical depth, the horizontal extent, or the full effects that it has on convection and aerosol transport. Right now, the only real consistent and readily available long-term data set that we have within the boundary layer comes from our twice daily radiosondes that the National Weather Service releases. This leads to a pretty big gap in our data within the boundary layer. These radiosondes are better than nothing, but since they leave such a big spatial and temporal gap, it makes studying features within the boundary layer difficult. This leads to most research and investigations of sea breezes relying on numerical weather prediction models, which a lot of us know come with their own issues and nuances. These data limitations ultimately lead to the development of research projects like Tracer to help fill in the data gap, even if it's just for a short amount of time. So Tracer, or the Tracking Aerosol Convection Interactions Experiment, took place throughout the greater Houston area. It consisted of a lot of sub-projects, which you can see a timeline and list of here on the right. But the main Tracer campaign started in October of last year and ran through September 30th of this year. The main goal of the overall Tracer campaign was to capture high temporal and spatial resolution observations of convective clouds so that we can ultimately better understand the convective cloud life cycle. We also wanted to observe a wide range of environmental and aerosol regimes, for which Houston makes a really good location for this because it's influenced by several different pollutant sources. The hope is to advance the fundamental understanding of updraft kinematics and microphysics, and to improve the representation of deep convection in multi-scale models. To achieve these goals, a vast array of instrumentation and manpower went into these campaigns, and this has provided a ton of different data sets for analysis in the future. The sub-project that I'm a part of with Drs. Klein and Smith is Tracer Cubic, or Coastal Urban Boundary Layer Interactions with Convection. This campaign's intensive operation period, or IOP, ran from June 1st to September 25th. Our hypothesis going into this project is that the complex interactions that take place between the sea breeze and urban circulations affect the ABL structure, which can cause highly variable flow both spatially and temporally. We have several goals we're working towards, which include characterizing the sea breeze and its impacts on the diurnal evolution of the boundary layer structure, investigating how sea breeze and urban boundary layer processes influence aerosol transport and mixing into the free troposphere, and evaluating the impacts of environmental modifications associated with the urban boundary layer, sea breeze, and aerosols on CI. To help us investigate our hypothesis and work towards these goals, we deployed a network of ground-based kinematic and thermodynamic profiling units. including OU and NSSL's Clamps 1 and 2 platforms, as well as the University of Wisconsin's Spark platform. The locations of these platforms are shown in the figure on the right, and they're set up in a way to allow for a transect through Houston. Clamps 1 is located north of downtown Houston within an urban area of the city. Spark is located south of downtown Houston, still in a mostly urban setting, but with a more rural influence just to its south. And Clamps 2 is located at the University of Houston's Coastal Center, which is close to the Gulf Coast and Galveston Bay. These instrument platforms provide high temporal resolution data sets, and the spatial transect through the city allows for an increased spatial extent so that the evolution of the boundary layer structure through the city can be captured. Each platform is equipped with a Doppler lidar, an AERI, and the Clamps platforms have microwave radiometers as well. For this talk, I'm going to be focusing on data from the Clamps platforms and in particular the Doppler lidar data. So to get started with handling the several months-long data sets that we collected, I did a very quick and basic look through each day's data from each instrument on both Clamps platforms. I put together a table noting any data gaps or interesting features such as low-level jets or sea breeze features and signatures. All of this was done purely subjectively, but it allowed me to get a good grasp of our data availability and some interesting cases to look a little more into in these initial stages of data analysis. This snapshot of the table here just gives you kind of a rough idea of my method of going through subjectively to do this. Out of the 116-day campaign, we have roughly 110 days of nearly complete data availability, which is really awesome because half of our campaign coincided with the hurricane season, and luckily we did not have to deal with any issues from any hurricanes coming through Houston. As you have with any field deployment, we did have some instrumentation issues with a few different instruments. During the overnight hours, the lidar on Clamps 2 the lens on the lidar often got fogged up and led to a loss in data in the overnight hours. This occurred at Clamps 1 as well, but the time, it didn't happen anywhere near as often, and when it did, it was for much shorter time periods. So the data loss isn't as great at Clamps 1 as what we have at Clamps 2. We also occasionally lost the AERI after 18 UTC. I'm still not entirely sure what was causing that to happen, but alas, it did happen. Despite these data gaps, we still have a very extensive data set to analyze, and I'll show some of the initial findings as I move on in this presentation. Now, to get into some of these initial results from the campaign, shown here is LiDAR data from both Clamps 1 and Clamps 2 from July 18th. This particular day was what I'm calling a clear air case in which no synoptic scale features were in or around the Houston area and no convection initiation took place on this day. This setup is ideal for assessing the boundary layer evolution in a quiescent environment. A few features from this case include a very well-defined nocturnal low-level jet that you can see at C1. You can see the jet at C2 as well, but it's not as well defined as the location north of the city. Also overnight, we see a very clear distinction of aerosol layers with a much higher concentration at the urban site at Clamps 1. During the day, there's evidence of a weak sea breeze passage at C2 that occurs around 17 UTC. There's an increased southerly component to the winds, as well as increased updrafts and decreased aerosols. The sea breeze reaches C1 at about 21 UTC, which is particularly evident by the wind shifting from southwesterly to southeasterly. This case, as well as other clear air cases, can be used to gain a general understanding of how the boundary layer is evolving when no other large-scale features are around to influence the evolution. Next, I wanted to compare a couple of sea breeze cases. This case is from September 19th at Clamps 1, which again is located just north of Houston. The top panel on the left shows wind speed and direction. Within the black box is the timing of the sea breeze passage. The bottom panels depict wind speed and wind direction profiles, with the red profile showing the conditions an hour and 15 minutes before the passage, and then the blue profile showing profiles every 15 minutes surrounding the sea breeze passage. In this case, the sea breeze front moved through at about 2045, which was indicated by several changes to the environment. There was an increase in the near surface wind speeds leading up to and right after the passage, a clear wind shift to an easterly direction, and a rapid increase in relative humidity with a decrease in temperature as the cooler and moist marine air moved over the area. Many of these trends are also seen in this second case from September 23rd at clamps 2. Just after 20 UTC, there is an apparent wind shift from northeasterly to south-southeasterly. The increase in near-surface wind speeds is consistent leading up to and during the passage of the front, which you can see in the bottom left panel. What is interesting in this case is the big difference in how the relative humidity and temperature change with the passage of the front. This case has a very slight increase in relative humidity with a small decrease in temperature, then immediately followed by a decrease in relative humidity. During my subjective look-through of the cases, I noticed that discerning sea breeze days from non-sea breeze days at the clamps 2 location was much harder than at clamps 1. The increases in relative humidity and decreases in temperature at clamps 2 were significantly smaller compared to what we saw at clamps 1, which made us rely almost solely on wind shifts to be able to tell if the sea breeze actually moved through the area. This could be due to the proximity of clamps 2 to the coast, but it could also be influenced by the bay breeze from Galveston Bay. I don't know fully what exactly is happening yet. I still need to do some more analysis into these cases to be able to tell what exactly is driving these differences between the two locations. Another important and cool part about this particular case, even though we have this sea breeze that moves through in the afternoon, it is not strong enough to actually reach our clamps 1 location. So another important aspect of this project is to investigate cases where there is sea breeze-driven convection initiation taking place. On July 25th, an ideal case really presented ourselves for this. No other synoptic scale boundaries or convection were present within the immediate area. At about 17 UTC, CI occurs along the coast with the onset of the sea breeze front. These cells quickly dissipate as they move inland with the sea breeze. However, at about 19 UTC, which is in this bottom, just after 19 UTC, you can see on this bottom right panel, CI occurs again near downtown Houston. These cells quickly intensify and then dissipate by 2030 UTC. So they're pretty short-lived, but just because they're short-lived doesn't mean they can't drop enough rain to cause issues in and around the city. These two areas could be host to enhanced convergence as the sea breeze meets the different terrain and surface characteristics, leading to enough lift to produce these cells. These plots here are showing the lidar data from clamps 2 for this CI case. The left-hand figure shows wind speeds on the top and wind direction on the bottom. From these, you can clearly see a shift in the wind direction as the front passes, as well as an increase in wind speeds as the front moves through the area. This is indicated as well by the black boxes. The dotted lines in these figures show the timing of CI, which is co-located with both the increase in wind speeds as well as the increase in updrafts. So there are many complexities to consider when investigating the sea breeze, for which I plan to keep working towards understanding in the coming years throughout this project. The timing of the sea breeze passage and how far inland the sea breeze front penetrates are a couple of examples. We must also consider the characteristics of the sea breeze and its interactions with the urban land surface, since there is some evidence to show that these interactions could play a role in convection processes. We also want to investigate the effects of synoptic and mesoscale conditions on sea breeze boundary layer evolution and what role the sea breeze plays in the initiation of convection. So to sum it all up, the tracer cubic dataset provides several months worth of high-resolution data to examine boundary layer evolution within different environmental conditions. Our initial data analyses indicate several interesting cases involving sea breeze interactions and boundary layer evolutions. Moving forward, there are a few big to-dos on my list to keep making progress. These include finishing the processing of the thermodynamic profiling data from each platform, applying a sea breeze detection algorithm technique to qualitatively determine sea breeze cases, and characterize different boundary layer structures given specific synoptic regimes. Thank you, and I will take any questions.
Okay, so we can go ahead and open up questions both in the room and in the chat. So I'll go ahead and monitor chat up here, but if there are any questions in the room, we can feel free to take those first.
Do you have an idea of how many days a sea breeze was able to get to Klein?
To clamps one off the top of my head, I don't know. So right now everything's very subjective. So I have my table and I've subjectively listed days that I've considered sea breezes, but until I have a more qualitative way of assessing what a sea breeze day is, I don't have like a number to give. Josh?
This isn't a question, but this is just some good news. The AERI did not actually stop the data after you comes out. So there's just a processing code issue.
Okay.
And that caused it to click. So once that's fixed, you'll have data from AERI, from one AERI all the way to the day with like a 15-minute gap around 18C wherever it starts.
Well, that is very nice. Very good news to come back to.
I'm going to ask a question. So you mentioned that Tracer Cubic was part of a larger campaign. Do you think there are data sets from other sites or other platforms that will be important for your analysis?
Yeah, so there is a lidar at LaPorte, which I think will really help to supplement our data because the differences in location can help fill in almost like a square rather than just a transect. So I know that there's a lidar there. There is data sets, different surface meteorological data sets that I think could be useful to help capture wind shifts and changes in relative humidity. So there is a lot of different data sets that we can get both from the ARM site and also from some of these sub campaigns that are open source that I think will help supplement what we find.
A question in the chat. Have you zeroed down what algorithm you would like to use for sea breeze detection?
Not yet. While I was away, I know there was some talk about somebody who presented at the ASR meeting about using radar and satellite imagery to detect the sea breeze and then using wind shifts to nail down the timing. So I think something along those lines could be really useful, but I have not gone to dive into a particular algorithm at this point yet.
They say thank you.
All right, thank you guys.
All right, thanks everybody. And that's our last boundary layer seminar of this semester. As far as I know, this is at the same time next semester, but I actually have not confirmed that. So I will be on the lookout.